Hello to everyone, I'm Paolo Cremonese. I'm a PhD student at State University in Poland. I work in the Cosmology group here in Szczecin, and my work is focused on gravitational lensing of gravitational waves. Today I want to tell you about how the mass sheet degeneracy affects the lensing of gravitational wave and if we can break this degeneracy. The work that I'm presenting is available on arXiv and has been accepted for publication on Physical Review, and it has been done in collaboration with my supervisor Vincenzo Salzano and with Jose Maria Esquiaga. The mass sheet degeneracy is a well-known problem in the lensing of light. Let me first explain how this degeneracy takes place. So it consists on two sets of transformation. The first is to rescale the mass of the lens, as shown here, where I'm showing how kappa changes with lambda, where kappa is the dimensionless surface mass density of the lens, and lambda is the mass sheet degeneracy parameter. This parameter is not unobservable, but it describes the degeneracy. In particular, when there is no transformation, lambda is equal to 1. The second part is to rescale the position of the source, theta s, in the plot here, and the deflection angle alpha, as shown in the equation here again. So the important thing to bear in mind for now is that we are changing the source position and the mass of the lens according to some specific transformation described by the degeneracy parameter lambda. So now the problem with these transformations is that the observables are preserved. So if we have different set of parameters which give the same observable, this will introduce considerable errors when estimating this parameter, and consequently these errors will propagate if we are inferring other cosmological parameter from this lensing event, for example the Hubble constant. In the electromagnetic case, there are different ways to solve this problem, which always involve, though, further information apart from the single lensing event. On the other hand, as I will show, in some gravitational wave lensing events, we only need one image to break the degeneracy. So to assess how the degeneracy affects the lensing of gravitational waves, let's first see how we compute the lensing in this case. First of all, we have to get a waveform in the time domain. We obtain these signals from the PyCBC software. Then, computing the Fourier transform, we obtain the signal in the frequency domain, as shown here. Then, in the frequency domain, the lensed waveform is obtained by the product of the unlensed one with the amplification factor. This factor contains all the information about the lensing system and in particular about the lens. In this plot, we can see the comparison between the unlensed and the lensed waveform in the frequency domain. Finally, to get the lensed waveform in the time domain, we compute the inverse Fourier transform. And here we can see the comparison between the unlensed and lensed in white and black respectively in the time domain. So the effect of the lensing will depend on different factors that are described by the amplification factor. In particular, here we have the dimensionless frequency W, which contains the information about the redshift of the lens, the distances between the observer and the lens and the source, and it contains theta e, that is the Einstein radius, that is the usual characteristic length in the lens plane for a point mass lens. The point mass lens is the lens model that we are considering for this work. Then we have X and Y, that are the dimensionless image and source position. And then we have the information about the mass distribution in the potential. So from the transformation that we saw earlier, which give birth to the degeneracy, it follows that also Y and the potential psi change with lambda. And finally, also the amplification factor is changed by lambda. So how this amplification factor F changes with lambda will tell us how the mass shift degeneracy will affect the gravitational wave signal. Let's now see some examples of how these transformations change the lens waveforms, and let's see if we can distinguish the transformed waveform described by lambda different from 1 from what we call the original lensed waveform that has lambda equal to 1. So the first case we consider is the geometrical optics regime given by this condition here. However, we won't focus on this case because it is very similar to the electromagnetic one. Here, changing lambda only changes the magnification of the images, and the degeneracy cannot be solved if we do not have further information about the system. Then we have the wave optics case given by these conditions here. Here we always have only one image as the result of the lensing, which is modulated with respect to the unlensed one, as we can see from the example I'm showing here. So here the situation is different from before because the transformation with lambda changes the shape of the waveform and not only its magnification. Here I'm showing 3 cases for 3 different source configuration. The signal with lambda equal to 1 that we consider the original signal is shown in red, while the transformed one is in green. The differences between the 2 signals are subtle, but we can find some of them. For example, here we can clearly see that the 2 waveforms are different. But in general, these are small differences, and especially when Q is equal to 1, the top row here, there seems to be only a magnification difference between the 2 signals. But if we look at the frequency domain, the differences are more evident. So in the axis here, we have the frequency on the x-axis, and on the y-axis we have the characteristic strain of the signal. We can see that, especially in the inside, a change in lambda is not simply a rescaling of the strain of the waveform, and therefore the waveforms with different lambda are intrinsically different and could be in principle distinguished. In particular, in the insect, there is a comparison between the waveform with lambda equal to 0.5 and a rescaled version of the original signal. And we can clearly see that a simple rescaling does not give the transformed waveform. So the last and most interesting regime is the interference one. This stands in between the wave optics and the geometrical optics regimes, and it is characterized by interference pattern in the lensed waveform. This pattern is the visualization of the difference between the original signal and the transformed one. The parameter of the lens and of the source are described here at the bottom, but of course any combination of these parameters that satisfies the condition, this condition here, can be used to get this interference regime. So the case I'm showing here is given by a source at redshift 0.1, and we can clearly see that especially for times larger than 0, the 2 waveforms are really different. And the same can be said if we consider a source at redshift 0.5. Again, the two waveforms are really different. And the distinctions are also straightforward to see if we look at the frequency domain. So in this regime, even better than in the wave optics, we can clearly see the difference when we change lambda, meaning that we are able to break the degeneracy. The problem now is to set how well we are able to do that. And in order to answer to that question, we calculated the signal-to-noise ratio for the cases taken into consideration. So, contrarily to the electromagnetic case, to register a gravitational wave, we compare the data with a different template and we choose the best match. This is called the match filtering analysis. So, because of this, the signal-to-noise ratio is calculated comparing the signal with a template, as shown here, where we have S, that is the signal composed by the actual waveform and the noise, as we saw in the plot before. And then we also have capital S here, that is the sensitivity of the detector. Then we also want to define a confidence region through the delta Q squared, which represents the accuracy of the detection and consequently will set the errors on the inferred parameters. The value of the delta Q squared here for 3 sigma at 3 sigma is given by the fact that we are considering two parameters, the source position y and the mass of the lens. In this plot, I'm showing the signal-to-noise ratio normalized at the optimal value when lambda is equal to 1 here. And I'm showing how it behaves with lambda for different optic regimes that we introduced earlier. So when the signal-to-noise ratio curve leaves the confidence region, it means that the degeneracy is broken. The plot here confirms what we saw earlier. That is that the interference regime is the best case we can have, while in geometrical optics we are not breaking the degeneracy at all. This plot, though, does not give a proper estimation of the breaking of the mass shift degeneracy, since we are not considering how the source position and the mass of the lens change with lambda. So for a more detailed analysis, we computed again the normalized signal-to-noise ratio, but in this case in form of matrices, considering how the source position y and the mass of the lens, m of L, change with lambda. So here I'm showing this calculation obtained comparing always the same signal given by this parameter and this parameter, which give these two brightnesses. And I'm comparing this signal with different set of templates given by different value of the source position and the mass of the lens. And these values are given here in the labels of the axis. So let's say now that we want to recognize this signal, for example. If we do not take into consideration the mass shift degeneracy, we would infer that the source position and the mass of the lens are constrained like in the plot here, where the highlighted region are the confidence region. So for example, we would infer source position of 0.9 to 1.25. The problem is that, of course, we need to consider the mass shift degeneracy. So then we computed the signal-to-noise ratio, again, comparing the same signal, but with transform templates. So in particular, here, we found the minimum lambda for which we still have degeneracy. In fact, the original signal is inside the confidence region, even though the templates are transformed. So basically, what we are saying here is that we are misinterpreting a transformed template with the original signal. Then we do the same and we find the maximum lambda for which we still have the degeneracy. So eventually, doing like this, we can set the actual boundaries in the y and m of L parameters. And the errors are the following. So let's focus for a moment on the error on the mass. For this first signal, so if we have a signal to noise ratio of 11, this is the error on the estimation of the mass, and this error is actually larger than current errors on the mass that can be obtained by dynamics calculation from realistic errors on the dispersion velocity of the lens system. If we move to higher signal to noise ratio though, we can see how this error on the mass decreases a lot, and its value is lower than the value showed here. So this means that for this case, when we have a signal to noise ratio of 55, for example, the mass shift degeneracy is broken and it would not be the dominant source of uncertainty. So, to conclude, in this work, I showed how the mass shift degeneracy affects the lensing of gravitational waves. We saw the difference between the optical regimes, and finally I showed when and how well the mass shift degeneracy can be broken and what it means. If you have any question, I'll be happy to answer them during the discussion session. Otherwise, you can write me an email or visit my website for more information. Thank you all for listening. Bye everyone.